try to. So I'm going to talk a little bit about the simplest random graph and then move on to some more complicated random graphs. Spend a little bit of time talking about just describing the different algorithms that generate that, and then tell you what you can do with it, and move on to how we might do some different kinds of tests and such. So the basic question is, we've been spending all this time, energy, and effort collecting real data. Why do I care about random graphs to start with, right? So why do I need to make up data? The main issue is you have to remember when you get a network, you're often really doing a case study. I might have 1,000 individuals, but I have one network. And so if you want to think about doing inference or some kind of, get some sense of what's interesting about your network, you need a comparison to that network. And what happens, our random graphs end up being a really nice comparison set. So it's where we do our inference on processes on the graph. So are we getting more diffusion than we'd expect by chance, for example? Is the association between being a friend and having a particular characteristic more likely than you would expect for chance? These are the kinds of things that a random graph allows us to use as a background. It also allows us to do some things with sampling. So once we have a notion of what a random graph is like, we can use that for things like snowball sampling, or we can use it for things like thinking about how we might be repeatedly sampling from the network in a bootstrap sense. So we're going to start with the simulation model, just to build on some of the things that's been going on thus far. We often want to test our measures or our models against a collection of networks with known properties, right? And purely random graphs, it turns out, have very well-known properties, and so do the pieces of information that we have about more complicated random graphs. They tend not to be realistic models, right? So like we know that real networks are not random. That's the whole point. But they might have enough randomness in them to be useful for us. So the simplest random graph is known as a Bernoulli random graph, an Erdos-Renyi graph. These are roughly the same things. There are two formulations to describing the Erdos-Renyi graph. It's given a graph of n nodes, assume that all the edges have equal probability of being present. So imagine your big adjacency matrix. Each cell of that adjacency matrix has a probability of being on or off. You flip a coin at each of those sets equal to that probability, and you get a realization of the graph. In the limit, that's equivalent to this other idea, which is we choose at random from the set of all possible graphs with n nodes and m edges, right? Now, these are not exactly equivalent on small graphs, because on a random sort of coin flip, you might end up with m edges or m plus 1 edges or m minus 1 edges. But in the limit on the 9 set, it's the same thing. And the reason that we have this randomization approach is that this second one is really what we want. What we would like to know is, what does the universe of all possible networks with the characteristics we care about, say this number of nodes and this number of edges, what does this look like? And then we can compare our graph that we know is not random to that universe of all possible graphs that's in that set. The problem is, enumerating the set of all possible graphs is impossible. If you just take a network, you'll notice that this is a log scale, right? And this, if it were merely exponential growth, this would be linear in the log scale, right? So the number of possible graph realizations when you have networks of only 10 nodes, right, goes up dramatically. These are labeled graphs, so we distinguish A, B, and C from A, C, and B. But if you think of it, you get a network of 1,000 nodes, it's just literally impossible to have any sense of enumeration of this graph. And so what we're trying to do is to imagine the sample space defined by this set of all possible graphs. We want to draw from that in a realistic way and in an unbiased way. We want to get the parts of the network that are representative of this class of all graphs. So the simplest possible graph is this Erdos-Renyi graph. The Erdos-Renyi graph has some really nice properties. For one thing, we know we can write down explicitly what the degree distribution is going to be on that graph. Because if you think about it, every node has a binomial probability of being hit. And so this is the sum of a series of binomial trials. And the sum of a series of binomial trials in the limit is a Poisson distribution, right? And so we can figure those kinds of things out. We can write it down. And we can see, does my network have a negative binomial or a Poisson distribution, depending on how big of a mean we have. We can do that over and over again. We can figure out what the size of it might be. This is a larger graph. So in this case, I think I had 1,000 nodes with an average degree of 2.4, right? And so that generates a network of 1,000 nodes and 1,200 edges, right? So there's a person on each side of those edges. In this case, you end up with a giant component, a few little chunks, and a bunch of isolates. Right? So that's what this, on a repeated graph of this sample, this is what you'll get. Now it turns out that these random graphs have another really nicely known property. We hinted at this morning, which is that there's we know exact that if the average degree of the node is between 1 and 2, you're in the phase transition of a connected component, right? So if everybody in the graph on average has more than 2 nodes or two ties, then you know that if it's a random graph, it is connected. Right? So if I have a real graph where people have say 5 or 6 ties and is not connected, we know it's far from random. Right? So this is what we mean by saying comparison. We also know that if people have fewer than 1 ties, then it is possible. To have a fully connected graph, you have to have at least n minus 1 edges in the graph. So it would be everyone has to have at least 1 tie. But if you have a high level of connectivity you'd expect, it would be over here in this set. So this provides a random comparison set to what you might see in a real network. There are other properties we might care about, right? So imagine we care about the triad census. And so if you have a random network where I just flipped it on and off, this is that same network of 1,000 nodes, I get a distribution of observed triads, and because we know from a probability sense what the likelihood of A nominating B nominating C is, we can literally write down the calculation for what the expected number of triads would be in each of these sets. And we can see that in this case, we're not all that different. Because there's a 0 here, they give us a -1 there. But you wouldn't expect many closed triads in a network of this size and this degree, and in fact, you don't observe any. Right? This contrasts with a real network. This is one of the real networks in NetHealth. I don't remember which one this is, but here the expected graph at random is still, if it were a random network, you would never see any of these, and in fact, you see a lot of dense triads. Right? So this tells us that this is one way of thinking about the comparison of the observed graph to a random graph. Please.
A question back from your earlier slide about the random graphs having that they had to at least have 1 tie.
Yeah.
Don't you, like if you're mapping a collection of a system of people, there will be some isolates, right? Like people who aren't tied.
Right. That if you want to have the minimum requirement for what I should have been more clear. I spoke too fast. The minimum number of edges required to link everyone in the network would be n minus 1 edges total. So if I needed to, if I were trying to construct what's known as a minimum spanning tree of a graph, that's the lowest possible density. So I couldn't, if I have density lower than that, then I know my graph can't possibly be connected. And so in a real graph, a lot of those edges are redundant. They're flipping over. And so you're going to actually have isolates if you have a density higher than that. But I know density can't be lower than that. John?
Maybe a silly question, but are you assuming a tie probability of 0.5?
No. So what I'm assuming is a tie probability, actually in this case, I'm assuming a tie probability of 0.0024. So each edge has a 0.0024 probability of being on. Completely independent of every other one. And some nodes are going to have high degree, right? And so that on the tail. Most are going to have 1 or 2, and there'll be a few with 0.
Okay. Well, just one follow-up question. Is that sort of a term of art to use the probability at that level? Just because I'm thinking of when I'm simulating this maneuver thing, how do I choose what probability I want for my generative?
Yeah, normally what you do is you'll pick your probability so that the sum of the edges equals, say, whatever you're trying to compare to. So the most common thing to use a purely random graph for is to say, I've observed a network with a density of 0.24. Now let's generate a random network that has a density of 0.24 and see how they compare on other features, like the centralization or the triad census or something like that. And we can imagine, thinking that if I observed an health network with quadruple that density, that I can compare it with some other set. So another question was up on the left? Okay, awesome. So really is a bright projector. It's like in the headlights. All right, so the triad census is another example that you can pull out of this, and we can do that automatically. Now it turns out that, of course, a purely random, uniform random graph across the entire population is silly. Most populations have structure to them that are known a priori. So we know that you're more likely to hang out with 7th graders if you're in junior high than you are with seniors because of the building and the class structure and the other side of foci that sort of organize social life. And so what we might want to do is say random controlling for some of those features that we already know. And so the simplest features to correct for are these things called mixing. All right? So we have categorical mixing. In this case, I've coded this particular network by the self-reported race, and so people can self-report as white, black, Hispanic, Asian, other, mixed, and I've collapsed the other three in this set to a three category racial group. And so we have African Americans in green, whites in yellow, and others in red. And you can see there's a rough racial segregation, a racial separation in this network. We have African Americans here, whites over here, and the reds tend to be distributed relatively uniformly across the set. And this is the density of each submatrix of this network. So if you can imagine just taking the white kids and say, let's look at the number of possible ties between a white student and a white student, and then count up the number of observed ties from white students to white students, I see that you get about 1% of the possible ties are here. Among black students, you get about 0.8%. Among other students, you get about 0.6%. Right? So this is the probability of an in-group tie for whites, blacks, and others. And the probability that a white student nominates a black student is 0.001. The probability that a black student nominates a white student is 0.001. Right? So these don't have to be as close as they are. They're not exact because it's a directed network. And in some cases, it might be that. So we find that others nominate whites at a lower rate than whites nominate others more often than others nominate whites. Right. So this is literally we take the observed network, we count up the 465 students that are here, we sort them into the whites, the blacks, the others, and calculate the density of each subpart of this matrix. There's a question going up, please.
But this is a random?
No, this picture is the observed school.
Well, that's like a real.
Yeah. So this is a real school. Yes.
I thought you were creating a comparison map that had some
That's
correct probability.
That's right where we're going. Right. So what I've done is I've observed this in the real data. Right. And so I've gone out to AdHealth. I've just pulled one of these schools at random. Not quite at random because I didn't want to get the school that was completely odd. But so I picked a school that had some separation, but not super strong separation. And I then generate this set. And now what I might want to do is say, well, let's generate a random network that has this same look to it, that matches on that feature. And so I can do that. I can go through and I can create I can just randomly generate a network that's the same size, partition it in the same way, and then generate random connectivities at the same level. Right? So I just flip a coin with the weight of 0.096 in that section, 0.0016 in this section, and so forth. And so this is a random network that matches on the mixing and on the volumes. It has the same number of edges and the same pattern of mixing, right? But it still doesn't look quite the same, right? So you notice in this case, you get a stronger sense of segregation between race on the green on the top and yellow on the bottom, whereas over here you still see some of that, right? You see that there's if you squint, you see more green up here and more yellow down here, but it's clearly missing something because otherwise it's this big hairball, right? And so there's other structuring features going on in the real network, and those tend to be things like grade and reciprocity, right? And those types of things that are pulling the edges to look more sparse from an edge standpoint than they do here. The other thing is the degree distribution ends up being different. So in the real network, right, in the observed network, we get this long-tail degree distribution. There are a few kids that are much more popular than we would expect if it were just a random Bernoulli graph. So even though I've matched on the racial mixing profiles in these two cases, right, there's still other things left over that are telling us that even controlling for the volume and the racial mixing, there are still features that are unique to the real graph that aren't there in the natural graph. So you can see where this goes, right? So now at first I was controlling only for volume, then I started controlling for racial mixing. Maybe I want to control for other things, right? I can control for out degree, I can control for in degree, I can control for reciprocity. These are all different ways of constructing random graphs in order to match the real world as best we can to see whether there's any sort of variance left over. And if there's not, then essentially I can say that with respect to those attributes, once I've controlled for that, everything else is random. And that gives us a way of doing it. Now, it turns out, in practice, that's a lot easier to say than it is to do, right? And if you ever thought that this might be the case, imagine anybody ever plan a wedding, right? You got to seat people. So there's a random assignment problem in wedding planning. You have to put people at tables such that everyone has a table and no one has a fight, right? And so they're all talking to each other at the end. And so what you might find is that if I put Grandma with Aunt Bessie, at some point I end up with Uncle Art that has no one to sit with, right? And this is what happens when you do these kind of random mixing features. That once I've controlled for, who's played Sudoku? Right, so Sudoku is a really specific matching problem. where there's really only one assignment of numbers to cells that will match the conditions on the edges. In this case, there's lots and lots and lots of assignments that will match the condition of fit the right number of edges in the network. There are a smaller number of assignments that will say fit the right number of edges within each one of these cells. There are still fewer arrangements that will say and keep the out degrees constant, and keep the in degrees constant, and keep the reciprocity constant. Before too long, it gets really hard if I can think of the graph building process of adding edges to an empty matrix. At some point, I'm going to make some assignments that make it impossible to do other assignments. And so all of the trick of generating random networks that sample uniformly from the set of all possible graphs with the conditions that I care about is finding a construction rule that doesn't walk you into a weird part of the space that's easy to build but not representative of the entire set. And so there are a couple of tricks to doing this. My favorite trick is what's known as the zipper method. And the way the zipper method works is that you can imagine if I have something like a degree distribution, I have two people who have degree 1, I have two people who have degree 2, and one person who has degree 3. And so what I do conceptually is I generate a series of half edges. And so here's a person that has degree 1, so A has degree 1, and they're not tied to anybody yet. B has degree 1, they're not tied to anybody yet. C has degree 2 as one of my degree 2 people, so I just add 2 C stems out, 2 D stems out, and 3 F stems out, right? So these are the half edges. Now I take this thing, I split it in half, right, where I put randomly choose half of them as senders, the other half as receivers, sort them, zip them together. And that's where the zipper language comes from. Because I've zipped them together, because of this little trick of making sure that I have all the half edges right that are right on degree, they're going to be right, the degree distribution is going to be matched. And this works brilliantly. Right? It's almost magical how well it works to match on degree distribution. It turns out that it also works really well on mixing, because I can say degree same race, degree cross race, degree what have you, right? I can have in degree versus out degree versus mutual degree. And so you can concatenate these different features and do this same trick to generate a random network. And because the input to this is purely a random sort on a uniform list, you know you have a reasonable sampling across the entire space. And so it's a very nice, easy, quick trick to do this. It's much easier to do when you have a natural distinction between senders and receivers, right? And the reason for that is that if I'm trying to do, if I'm doing a purely heterosexual network, I can say here are all the men's degrees, here's all the women's degrees. A beautiful thing about a natural network is that because men are connected to women, the average degree of men has to equal the average degree of women. And so I'm going to have enough edges on one side to map to the other edges on the other side. If you do this wrong, right, you can end up with an odd edge hanging out here that doesn't have anywhere to go to. Or even worse, which happens more frequently if you have small networks, you can mean the only assignment that would work would be F tied to himself. Right? And so you have to, there's some tricks you have to play that, particularly if you have small networks, to make sure that that doesn't happen. For really big networks, that tends to not be a problem. In really large networks, it's such a vanishingly small probability that this person is tied to themselves and you don't have to worry about it. So that's just a hint of how these things work. This is the kind of thing that might happen. So this is data based on, I just took the Colorado Springs degree distribution and said, let's imagine that we had, instead of a population of a few hundred, let's imagine we had a population of a few thousand, right? And so you can then scale up from that sense and see what that might look like. Now the other thing about these kinds of, is that a question? Sorry. The other thing that happens with these kinds of random graph models is it turns out that some of the features we can write down. So because it really is a choice probability set, I can say what's the probability of getting some structure knowing something else about the network. And these are known as conditional probabilities. And so this was just a picture from the graph I showed a minute ago. Payek, the program, generates the expected number of triads for a Bernoulli random graph, right? No conditionals. But we actually know analytically the formulas for the expected number of triads under what's known as the graph given MAN, the number of mutual, asymmetric, and null ties. So given that I'm trying to hold constant the number of mutual ties in the network, the number of asymmetric ties in the network, and the number of null ties in the network, I can then generate what the expected value would be given that distribution. Right? And that's we know in closed form. Turns out the formulas are really, really, really ugly. They're not complicated. They're just really long and tedious. But we know them. It's there. We can do the same thing. We can write down in closed form the expected value for the triad counts for the for the random graph given the out degrees, given the in degrees, and given both, for example. But we can't write down in closed form the expected value of triads for the number of out degrees, in degrees, and mutuals, for example. Right? So that, we don't know how to write that one down. That we have to simulate. And so this is where we're kind of at the edge of these different sorts of random graphs. Why would you want to do that? Well, it turns out, just remember again, this is the most important part of networks. Right? Okay, we're all with me. If you get nothing else out of other than this week, then the triads are important, then we've gotten something. And why are they important? Because if we think about collections of these triads, they encapsulate each of these triads encapsulates some kind of a micromechanism. That micromechanism tells us something about the social processes going on in the setting. And we can compare then the observed count of triads in a given setting to what we would expect under random chance. And that's what this little box plot does for each triad in the ad health data. We can see that we have a lot more of this triad than we would expect by chance, a lot more of this triad, a lot more of this triad, a whole lot more of these two triads. Right, and this tells us something about this is the box plot for all 129 schools in ad health. They tend to avoid these kinds of triads. They tend to seek out these kinds of triads. What social process maps onto that? And this is what's nice for us. It's not that we think that the random graph is a good model of what the world looks like, but it's a good thing to sort of help us not see the things that don't matter and focus on the things that do. Now this is comparison to the dyad distribution, the MAN distribution. We might rather compare this to a more complicated random graphs. They say, because we know that kids, if you imagine taking kids and forcing them to be in 3-person classrooms, right, that would force me to generate lots of clusters because I'm going to call you a friend if I hang out with you long enough, right? So social settings can generate social relations just by clustering through focal points. So we'd like to account for something like that. So we might want to know the number of clubs we share. We might want to know if they're the same gender, the same grade, or have a teacher in common, or both like ponies, right? So there are kinds of things we might want to control for that we think drive associations, in this notion that people might want to have a dominance hierarchy or something. Is there anything left after controlling for those other kinds of sorting features? And that's what you need models for, and that's what we're going to talk about here. That's what ERGM allows us to do. ERGM allows us to specify the probability of a tie between any pair of nodes in the network, controlling for all the other things that the two nodes in that tie potential share. So to create the probability that John and I are connected, controlling the fact that we both use SAS, we both think networks are cool, and we both go to Duke, right? It might not matter at that point that we have third friends in common, right? That could just be epiphenomenal. And this is the intuition behind these kinds of models. If you do that with the ad health data, or the Prosper data, in fact, just to give you a sense of the way these triad models work, we can write down, remember, these different models to say that that if we have a certain set of triads and only that set, not the others, we're certain to have a certain kind of hierarchical structure, for example. Once we know the random graphs, we can figure out for lots of different hypothetical models, right? The models that say that everyone is either close friends or enemies would be the first one versus a very complicated hierarchical structure on the last one. We can compare that to what we'd expect under random distributions using something a lot like a t-statistic. And that's what this funny little formula called the tau is. We have some weighting vector, which says these are the triads that we hypothesize to be active or not. We've observed the number of triads in each of those 16 categories. We know the number of triads we would expect under random mixing, right? And because triads, if you and I share an edge on a third party, there's essentially a covariant structure to triad counts, and that's what this is. Well, if I take the difference between an observed minus its mean divided by a standard error, that's essentially a t-statistic, right? So that's what all this is. It's a vector version of a really big t-statistic, but it lets us think about the likelihood of seeing a particular pattern of ties in a network. And so in ad health, it turns out that the largest, sort of the most significant, the most signal we see in these settings are for this hypothesized structure known as a ranked cluster structure, which is that one I showed you at the first, where you have multiple different channels, multiple different layers feeding into a central core at the top. For the Prosper data, where the kids are younger, you actually don't see quite the same structure. So the ranked cluster structure is this kind that sort of ultimately leads to a peak. you see some signal as opposed to noise, but you get a better fit from these sorts of structures over here. These are 6th, 7th, 8th, 9th, and 10th graders, and what characterizes these structures are that they tend to have at least 2 separate distinct groups, which are probably boys and girls. Right? So for young kids, you see this distinction between boys and girls that then starts to dissolve as you get into the high school areas. Right? And this is the kind of thing that makes these random models useful, is you can think about your settings in terms of different types of features. And the triads, just because I have a bias for them, are the ones that I compare to, but it might be that you're interested in path length or overall clustering or something like that. Why else might you care about random graphs? It turns out that there are a lot of things about social networks that are on scales that we can't possibly measure as networks. Right? I would like to know something about the connectivity of the world as a whole, but I can't get all 3 billion people to fill out a survey. Right? And I wouldn't know what to do with the data if I could. So instead, we might want to hypothesize a social process on an underlying random graph that's constrained in one way or another and ask whether or not what we observe seems consistent with that or not. And that's the logic behind the small world studies. And so in the small world studies, we've discovered through various and sundry surveys that people can find another person in about 6 steps. Right? It turns out that it's not exactly 6. It's actually a function of the size of the graph. It's sort of the log of the size of the graph. But in principle, that number of 6 is not an unreasonable estimate. And if we want to decide whether or not that's a big number or a small number, we can compare it to the fastest case potential, right, where this is the old telephone tree that my mother used to have. Right? That kind of process would reach the entire world in 2 or 3 steps, whereas if you were to take a random network, what happens is I call some people, and some random subsample of my friends are also your friends. And so that creates a probability of us having overlapping friends, and that overlapping friend probability means that some of these ties are not going to be perfectly efficient, but we're going to reach a certain number of people in 1 step, something less than the perfect efficient in 2 and 3 and so forth. And again, because these are simple random probability exercises, we can write down exactly what we would expect that to look like under random expectation. So the random expectation, if everybody in the population has 2 steps, we would get a trace from the number of people you can reach in 1 step is just 2. In 2 steps, on average, you'd reach about 4, right? And then 6, and so forth. But because of the redundancy, you don't double each time. If I have an average degree of 4, I reach a lot more. And you'll notice that the degrees don't have to get very, very large before you rapidly meet everyone in a small number of steps. And that's because you're past that threshold, right? So if you're past that threshold of generating a giant component, then you can imagine what it would take to generate a giant component at just 1 set. That would be everyone having an average number of 2. Now layer over another giant component on top of that sort of is an independent second one. That would be degree 4. Layer another one on top of that, that's degree 6. Layer over another one, that's degree 8. Right? So you get these random networks. Each one is shortening the number of steps between each and every other person. And so as you get really high degree, the number of random steps it takes for me to get from any one person to any other person drops dramatically. And so the returns to a distance for random graphs can be very small. But the beauty is we know what it is. And again, we can compare it to observed networks, right? So I can know from the formulas what I would expect to see on average in a random graph with the degree distribution that matches one of my ad health schools. And then I can take each kid in turn and generate the actual trace curve. How many people would they see over time? And get an observed distribution, and you find that you don't reach as people as quickly in the observed network as you do in the random network. Why? Because friends of friends tend to be friends, right? And if my friends are friends of friends, then I don't have that broadcast sort of feature as quickly as I might in other settings. Just because I can't help myself, this is the actual data from the Milgram study. For those of you that don't know the small world study, did everybody know the small world study? 6 degrees of separation? Right. So the idea is that there was a stock. How long would it take a random people to reach a stockbroker in Boston? And so they picked people at random from Boston, people at random from Nebraska. I've forgotten that, Jeff. It's from Nebraska. And stockbrokers from Boston, and see how fast they would take to reach them. And they used the number 6 comes from the Nebraska sample. So on average, it took the people from Nebraska 6 chain lengths of size 6 to reach the stockbroker. Notice the sample size here. Right? This is the highest return sort of scientific finding ever. I mean, for an investment of 18 people, it's kind of remarkable. But anyway, and it turns out that these chains were not independent, right? What happens is a lot of people end up converging on the same people, who must have been exceedingly tolerant, like survey response people, right? Because about the 15th time I got a postcard in the mail saying forward it on to this joker. The logic behind this notion of a small world was then sort of writ large by Duncan Watts. Watts and Strogatz published a really nice paper in the early 90s, late 90s, on this process. And it's a nice example of what you can do with random graph, thinking through random graphs in large settings. And so what they thought of was, imagine you have a really, really big graph, like on the order of billions, but the network is really sparse. So people aren't connected to billions of people. People typically connected to at most hundreds of people. Right? So it's orders of magnitude, many orders of magnitude smaller than the network. The network is decentralized. You can't just go to Match.com and find the person, right? You have to have, it's actually a search process. And the network is highly clustered. Most friends tend to be friends with each other. In that setting, it seems really weird that you would ever find it possible to get from a random sort of parts of the world out to a single target anywhere. And the way they were able to make their career in some ways is they did a beautiful online experiment and show that people really can do this. So people are good at getting a message to people that are a target they shouldn't know otherwise, very rarely directly. And so I'm not going to walk through those pieces. I'm going to walk through the logic. And so the toy model that they use was to say, imagine that feature. If most people's friends are friends with each other, then you can imagine the worst case scenario would be everybody lived in small, tiny cliques, little caves that they lived in. They called this the caveman graph, where the most connections you would have would be a small number that might link caves to each other. So if this were the case, the number of steps it would take for me to reach someone else is directly proportional to the number of caves I have that would lie on this cycle. And so if you have billions of people in 5-person caves, it would take billions of steps to walk around that circle, right? Instead, then, what we find is that you can imagine we know that that's not how long it takes. It takes a lot fewer steps to reach from one set to the next, and this is what we find interesting. And so they ended up coming up with a metric that said, we'll compare the number of steps it takes to get from one person to the next to the number of steps it would take in a random graph. And we'll compare that to the amount of clustering we see in the network compared to the amount of clustering we would see in a random graph. And what characterizes the small world problem are that there are some settings where the clustering in the open boxes here is really high, but the scaled path length, the number of steps it takes, is really close to what you would expect under a random graph. This is a situation that characterizes the small world. In a small world, most people have lots of clustering. We recognize it, we see it. There's a lot more clustering than we would expect by chance, but the average number of steps from one person to the next are just about as big as you would expect to see by chance. And you can get an intuition for why that's so by imagining your caveman graph again, but now randomly add a few ties to it. By randomly sprinkling a little bit of noise in this otherwise highly structured network, you create shortcuts. And those shortcuts quickly reduce the distance in the overall graph to make it very similar to a random graph. And so that means then that the distance distribution looks like it would in a random graph, whereas the local clustering is much higher than you'd see in a random graph. And that's what they use to explain this phenomenon that we can get around the world quite quickly. It turns out that we can write down, again in closed form, the expected value of the random graphs for the average length and the amount of clustering, and then compare that to a series of observed graphs, and in almost all cases, right, real networks tend to have a path length that's pretty close to this and a clustering that's much higher than this. Now, just as an aside, the original papers here were fundamentally flawed, and they were one-mode projection of bipartite graphs, and so you got a lot of clustering, and so the random modeling of the clustering was actually overestimated by orders of magnitude. But even once you've corrected for that, this seems to be true. Now you can flip this process around, which is kind of nice, and say, well, all right, that tells me something about characterizing graphs as a whole. Maybe if I know something about what the patterns of connectivity look like in my network, it would tell me something about who could reach who, right? And so this is known as the network scale-up problem. And in the network scale-up problem, I have some total population I know how many people know certain kinds of people, and then I can estimate essentially the connections between people in the population to everyone else in the population. So the classic example might be something like how many people know somebody who was killed in a war, right? So I know there are 300 million people in the population. I know how many people were killed in the war. I know how many friends on average people have. I can from that calculate the likelihood that you know somebody that was killed in the war. Right? And this is really useful for ways of thinking about things like viral marketing, whether the messages get out or so forth. The original model is literally just using the probabilities of this kind of a random sort of mixing set. So imagine people have a certain amount of ties that fall on random, and so that we can then scale up from the number of Joes they know or the number of war dead they know or something and get these kinds of proportions. Newer models actually build in a capture-recapture kind of model that allows us to take into account lots of mistakes for data and lots of knowledge that people have, and much more realistic clustering. Matt Selganic and the guy at Washington, I'm drawing a blank on his name, Tyler McCormick, have done the most work on this recently, and they have some really nice Bayesian models for what's known as the network scale-up problem, which lets you then reverse it and say, given that a person knows 15 people on average that have been in prison in the last year, that tells me something about how many people they must know writ large. All right, so that's just a quick overview about the way that random works, what a random graph is, the way we might construct random graphs, and the way we kind of use them. Questions, thoughts, comments, concerns on those? That's hopefully enough to get you to the random graph models we're going to talk about tomorrow that are really, you can imagine them being simple random graphs with many, many, many more constraints, where instead of doing it algorithmically by sorting it, we're going to do it parametrically by identifying parameters that we can then do in sort of a logic sort of sense. All right. Now let's think about another use for random, which is this idea of inference. Bless you. Those who aren't from Carolina might be surprised at the pollen counts that happen around here. A friend of mine in graduate school sort of made it through her entire career without having to be on meds until it was time to write a dissertation in the spring, and just couldn't think anymore. She might not have liked her dissertation, but the sneezing didn't help. So remember the problem of inference back from your first statistics class. The thought is you observe a parameter, and you want to know whether or not that parameter is different than 0 in the population. So the question is, we want to take this parameter, we know what its value is. Given the sampling variability and the size of our sample, can we believe that value is anything other than 0? And so we're going to construct a confidence interval around it. And if that confidence interval says that we're going to repeat this sample a bunch of times, 95% of the time the value would be above what we might expect or above 0. And that's the general idea, is that we're trying to infer from a sample. The notion of inferential statistics are to infer from a sample to a population. If I had the population, I would never have to add a standard error, right? I could just go and say this is the value, right? This is what it is. And so you might say, if I have a network, which the first assumption of a global network is that I have the population, I don't care about inference. Right? So you write your paper, it's a brilliant paper, you estimate your coefficients, you don't put any standard errors on them, you send them off to the journal, and they write back and say, you're out of your friggin' mind, right? And the reason is there's another inference problem. And the inference problem is that there's fundamental uncertainty in the world, right? And that fundamental uncertainty is not just about sampling uncertainty. It's not just trying to move from the sample of the data we have to the population. It's also about whether or not the underlying social process is generating something other than a random process. Are we picking up anything from rather than random noise? And in networks, it turns out there's a lot of sources of random noise, right? As you remember that survey that the students in Ed Health filled out, the fact that any of them were able to actually fill out that bubble Scantron sheet, you know there's error in that, right? There's error in the matching, there's error in the sampling frame, there's error on the day that I'm there, whether I'm happy or sick. Right? So there's all kinds of sources of variability built into that set. There's also sources of variability in the underlying association, sort of the fundamental association between elements. It's not necessarily certain that just because I smoke I'm going to get cancer, right? There's a certain amount of random probability in the world, and we expect that to be the case for any sort of network association as well. But that kind of random probability sense means that the associations we observe may not be certain, they're not fundamental, they have some sort of amount of variability to them. And so we'd like to characterize that variability. And so what we do is we change the inference problem a little bit. We say, let's imagine a social process or a mechanism process that could create an association known to be random, right? So we sort of take the counterfactual to say, I want to figure out whether or not smoking is associated with being a friend. If two people are friends, they both smoke, I can generate that correlation. Now let's imagine that I've assigned smoking to people at random. Would I get a different association in the network, right? And so what you're doing is, by construction, you're creating a random hypothetical, right? And then you compare your observed data to that random hypothetical. Let me make it concrete, and I'll give you a quick example here. These are data on families who married each other in the 14th century. Just I wanted something really relevant for today. And so we ask whether or not the fact that these two families are married to each other, do they also go into business together? And this is a standard data set that's sort of out in the social networks world. And if you do that, you can get a pairwise correlation of 0.37. Now, what do I mean by a pairwise correlation? What I mean is you take this matrix, right, you string it out as one long vector. So I have a column 1, which is the dyads. You're just going to have n squared dyads, which are now they're married together. Another string is going to have n squared dyads that is equal to whether they do business together. And I just correlate the first string with the second string. That's not actually n squared, because I usually don't look at the diagonal. Excuse me, I don't look at the diagonal, but that's the basic idea. And so the correlation then between the business vector and the marriage vector, in this case, is 0.37. And I'm using a Pearson correlation, but you can use any kind of correlation you want. It doesn't really matter. So is that a big number or a small number? Right? If your network's really big, right, then by random chance alone, we're going to find the case that the Medici group here, they marry lots of people, they do business with lots of people, right? So you're going to get a certain amount of overlap in these two matrices just by the fact that there are differences in volume across the different rows, right? And so what we can do is we can do this thing called quadratic assignment procedure. And in a quadratic assignment procedure, you take the original data, right, that is sorted by A, B, C, D, and E, and you resort it. Please?
What if you have, say in the back example, you had the Florentine families, and I know you have the Florentine business, but what if you have only a subset of the families in the business network? I mean, is that just simply taking a subset in the marriage network, or do I have to do something different because I have different size matrices?
You would have to do something to make your matrices correspond in size. And there are a couple of options for this, but the QAP model by itself has to have corresponding matrices. Essentially, what you're going to think about is that you can think of it as a classic missing data problem, right? So I could expand the networks to their both maximum size, look at the corresponding cells, and some of these cells will have missing values, right, if you go through the dyads. Now, you can decide to treat that listwise, right, and get rid of all those dyads, whether it's possible. You could treat it pairwise or what have you, whatever your standard missing data is. And it turns out that we can use some of the same random graph models to infer ties from the pattern of other ties. So if I know that it turns out there's a very high association between being friends with a cross-sex person and having sex with them, then I can use that information to get the probability that two people who are also friends have had sex. Turns out in AdHealth that that's what we thought we could do when we collected the data, because it was really hard to get the REB to let us do sex. The correlation is not there. The two events are in totally different time scales. But that's neither here nor there. Well, maybe. So you do this permutation test. So I have one matrix, and I have another matrix. And all you have to do to figure out whether things are associated or not is break the natural association between them. So the data were given to me one way. I take that data, and I just randomly permute it. So I randomly permute the rows, and I randomly permute the columns in exactly the same way, right? So you have to make sure the diagonal stays the same. But by doing that, now one matrix, its association with the other matrix is completely made up. There's no natural association. The only association is going to occur because of some volume features in the inequalities in degrees or so forth. So the QAP process is a classic, wash, rinse, and repeat. So you do your correlation, you randomly sort it, you calculate it again, you store the outcome, do that as many times as you have patience for, and you compare the observed correlation to the outcome. And in this particular case, if you do that about 500 times, the observed correlation it ends up being centered on 0 in this case, but you can sometimes get correlations up into the 0.15, 0.2 range, and the observed correlation is way out here. So what this tells us is the random probability of observing a correlation as big as 0.37 is exceedingly unlikely given a network in a world that was generated by an underlying random process. Now, that was an underlying simple random process. I could have a constrained random process. I'm only going to sort people within grade, or only going to sort people within sets. So I could continue to constrain this, but the logic is the same. And the beauty is the logic of this applies just as well for bivariate correlations as it does for logit models. Right? I can calculate a logit model on the dyad, controlling for a dozen different things, permute the dependent variable matrix 1,000 times, re-estimate the association, while holding constant all of the correlations amongst the independent variables, and get an estimate of the association between the thing I care about the most. Right? And so these kinds of tools are really effective for doing those things. And so UCINet does this directly. So there's a tool for doing this in UCINet across lots of different correlation structures. There's also a package in R for doing this. I'm not sure I have it here. My favorite package for doing this is coming from John Levy Martin. His package is called DAM, for Dyadic Analysis of Matrices and Networks. If you've never met John Martin, he has a certain sort of flair about him. But again, you can do this for lots of different things. This is just an example of what a regression might look like. I'm going to figure out whether or not there's an association between being friends and being the same race and the same sex. In this case, the shape of the network versus the, is that what I'm doing? No, I've just made up a dependent variable. So I've made up a dependent variable here, which is y. And so if you want to use this QAP in its classic form, what you do is instead of modeling y directly, you treat each dyad as a different score. So I can say that person 1 and person 2 differ. They're 0.277 distance. So I have to add 0.277 to 0.32 to get 0.59. So that's how different these two are. And I can go through each pair and I can say how distant a pair is in the network. And then I can use that distance dyad as a dependent variable in an OLS on the dyad level, do this permutation thing. And I show that if you're the same sex, you end up being a little less distant on the dependent variable than you would be otherwise, but it appears not to be significant. That is, it shows up about as often as you'd expect by chance, and there's about 86% of the time the observed statistics are as large as you would get in your observed network, but that's not true for the random network, right? So for the friendship tie. So being adjacent to the friend ends up giving you a very low standardized, low distance in this dependent variable. And in fact, you'd almost never see that in the random permutation. So this is how this works. And the nice thing about it from a statistical standpoint is that all of those assumptions you make that are simplifying assumptions to make your models converge, and about your random error terms and such, normal distributions and those kinds of things are gone. The only assumption you're making, right, is that this is the observed pattern compared to a world that is completely random in the way that you've randomized, right? Now, whether or not that completely random the way you randomize it is at all convincing, it depends on some of the other things you're doing in your setting. But it's a really nice way to break. It's because it's a non-parametric assumption. It ends up being a really nice way to sort of sidestep some of the inference errors and inference problems that come with standard model. In the far back, yeah.
Is there a rule about the number of permutations?
It's a standard law of large numbers sort of thing, and so it ends up converging. If you do 2 or 3, you're going to get some random weirdness. But if you do a few hundred to a few thousand, the difference is not going to differ that much. It used to be that these were really complicated and slow, and it would take you a long time to do. With modern computing power, I usually do 2,000 or 3,000 and don't even think about it. Right?
So there still is a linearity assumption here when you're using the
Yes.
regression models. Yeah.
So in this case, this is a linear assumption. You can, of course, construct. That's a great question. So your dependent variable in this case is a continuous variable. But I could imagine that I also had an independent variable that would have some kind of continuous thing. I could do an x and x squared if I wanted to get a parametric set. If my dependent variable was on or off, I could run a logit model, right? And so I wouldn't have to have a linear, essentially a linear probability model. I could run a logistic or what are those things called when it's not the logit, but it's the normal? Probit. Thank you. Jesus. Your brain goes blank up here. So so the linearity assumption is not necessary. That's a modeling choice, and you can specify any functional form of the model you want.
What was the adjusted R squared adjusted for?
In this case, it's adjusted for the number of other variables in the model.
Oh.
Yeah. It's a standard. I mean, this is under the hood, right? This is literally basic standard everyday vanilla OLS. But instead of dealing with I just throw away all the standard error calculations and instead use the permutation test to get them. And it's gotten remarkably easy to do now. So this is the this is the one reason that I keep. Anybody here from Kentucky? All right. Don't tell Steve I said this, but the one reason I still keep his program on my desktop is to do these models, because it is relatively easy to do. You can just read it right in. And they have more of these different kinds of permutation tests than any other tool out there that I'm aware of thus far. So including the ability to do correlations, which is what we just did, but also a multiple linear regression, a logistic regression. You can do with where you have a dyadic dependent variable or a node level dependent variable. It has all of these permutation test models in there. And so the one reason that it might be worth the headache to get out of the program you're used to working with and jumping into UCINet would be that these things run quickly. Again, it runs really well on a single network. If you got to do this for 150 different networks, it's going to be a pain in the neck, but it's there for the single network models. All right, so that's association models and permutation tests in like much faster than anyone should ever get it. All right, and we're just keeping up the theme for today. So the last thing I want to do is talk about this idea of a latent space model, which is a generalized class of ways of using parametric models for networks. And so this is the first, if you will, sort of way of thinking about networks that are later going to be dealing with in Ergams and Siena models. But the basic idea is you probably know this idea intuitively, which is that if you have an adjacency matrix, like any of your favorite adjacency matrices, where's a nice one? There we go. You can imagine this matrix as a dependent variable. And if you had to run this, if I just handed you a matrix and said, gun to your head, I need you to give me a model to predict this thing, what would be your first instinct to use? I have to come up with some way to quickly predict a 0 or 1 dependent variable. I says, Moody, all right, fine, you're crazy. I'm going to run a logit model on each cell of this dyad. Right? I'm going to string them out to dyads, and I'm going to run a logit model, friend or not. Right? That's all we're doing. Right? We're going to do that, and when at the same time respect the fact that these things that all of these dyads comes from this node, all of these dyads come from that node, and there's an association across a set of them. The logic there is that if we have each cell of this matrix, we want to figure out what the probability of a tie between any two people is. We have the probability that there's a tie between people, that you observe the network that you've observed as a function of some set of coefficients, some set of covariance, and this crazy thing, the z-statistic, which is a latent space. And the logic here is that you can imagine a network as encapsulating some unobserved social space. And if you and I are close in social space, we're likely to be friends. If we're distant in social space, we're unlikely to be friends. Right? And so all of this model is trying to do is building under the hood a logit model, right? Which is all this is when you work it through it at the end of the day, where I have the probability of a tie between any two people is a function of a coefficient times a series of covariance. That's your standard logit regression model. We're both male, we're both female, we're both sociologists or not. And the difference in our distance, right, the difference in our position in this underlying latent space. And so as this distance gets really big, right, we expect the hypothesis is coefficient, we should be unlikely to be friends. As this coefficient gets really small, we should be very likely to be friends. Right? And so what Pavel and Kravinsky and Mark Hancock in this sort of set, this is a somewhat fancier version of the latent space model, in that we're also going to add an indicator variable for being in the same group or not, which is coming up here, I think. So we can imagine that there's a series of groups from 1 to G, and we're going to let this latent space differ a little bit from group to group. That's a generalization of the overall idea. The original model was invented by Peter Hoff, who, just to brag, is coming to Duke as a new professor next year. We stole him from Washington. And so the Hoff model is the same model as this one without the kind of grouping that's built into it. But I just showed you this one to show you the kind of the series of things we can have. Now it turns out that Z can be as a space. It's not a single variable, right? So I could have a 2-dimensional space, I could have a 3-dimensional space, and I could have a 15-dimensional space if I wanted, right? And so it's entirely up to you to figure out whether you want to have a 1-dimensional space, 2-dimensional space, or what have you. Don't get carried away. All right. I mean, the vast, vast, vast majority of models that I've seen have gone to 2, maybe 3 dimensions, but if they tend not, you tend not to need any more than that. It's not that you can't do it. In some cases, you might. In the original version of this model, the user has to specify the number of groups in the network. So I'm going to look for 2 groups within the space, 3 groups, 4 groups. Hopefully, theory would inform this, but there is a fit statistic at the end, so you could search through the set, figure out what you have. But the kind of thing that the model ends up producing is that you have some probability of a tie between people, right, and an estimate of their location in the different dimensions. So here I have a 2-dimensional latent space, and I've observed where nodes fit in the space. This should look a lot like the force-directed layouts we've done before. That's effectively what we're doing. We're fitting the space as opposed to letting the springs tell us. Jen?
Is this for just whole network data? Is this for ego network data? Like, what are the restrictions?
So this is for global network data, but there are new models where you can have holes in the underlying data matrix, so you can have missing data. Jake, are there latent space models for ego networks? I don't think so, yeah. So the nice thing about it is it allows you to do not only, so remember this is a relatively general model, it allows you to have not just the difference in the latent space, but also any other observed covariates you want, right? So I can figure out whether or not we're, the logic here is that this part sucks up all that unobserved heterogeneity, making our cases interdependent, and so conditional on our position in the latent space, we can treat the covariates as independent effects, which is what's required of the model, right? So we can deal with that kind of what used to be an error problem of having correlated observations by soaking up that autocorrelation in this distance space. John, was there a question?
Yeah, so in the specification of the group term, what's the common practice to do that? I mean, are you running some other detection thing that all have this kind of groups, or?
I think that ideally you would do something like that. You would have explored the data a little ahead of time and say, well, it looks to me like there's a good reason to think that there are 3 groups here or 4 groups here. A lot of times I think people just keep fitting it until the BIC score, reaches where it needs to fit.
Comment.
Yeah.
This is essentially a mixture model.
Yeah.
So information criteria, I think, is kind of the general.
Right. Yeah. Yeah, and it's a great way to do that, right? Because it's built into a Bayesian framework. You have an empty chain under the hood. It sort of lets you fit all those kinds of things. Right? So the results look something like this. And so this is like this one happens to be built within the ergom package. So we say the Sampson data is functions as a latent 2-degree network, and the total fit is we're going to ask to write out there. I can write it instead by saying that we're doing the same thing now. This data set is my dependent variable. It's still a 2-dimensional latent space, and now I'm saying there's 3 groups built into this space as well, right? And so I like the fact the graphics that come out of this package. Like it gives you a position of latent space. It tells you where the centroid of the group is, right, and the distance between the groups. It's a very nice multi-level model in that sense. You can fit lots of them of different sorts. This is one of the Prosper datas, pieces with 3 groups, one of the small schools. And you can get Bayesian posterior predictions of where they fit, so where are the density profiles of these places. So they're kind of fun. They are I haven't done them in a while, so I don't know if they've gotten particularly fast. Last time I ran them, they were limited to smaller schools or smaller networks. I just haven't done it in a long time.
Still not completely following how the Z sets up error.
Mm-hmm. So imagine that I have a network that is perfectly embedded in a latent space, right? Such as, for example, a network that might look like, well, the best example would be to say that if I have a 2-dimensional space and I'm able that every time 2 people are friends, right, I can draw them in this space so that every node or every edge is exactly the same length, right? In that case, then the correlation between the geodesic distance and the screen distance would be perfect, right? I would know that if I'm 2 inches apart, I'm also 2 steps apart, right? That would be the perfect fit to the latent space, right? And so what the latent space is trying to do is identify the assignment on this dimension and that dimension that most closely approximates the perfect fit between the geodesic distance and the latent space distance, right? Now, it might be that I have a lot of ties like this that cluster over, in which case there's no way that I can get a good fit in 2 dimensions. But that's the beauty. I can do it in 3 dimensions. I can do it in 8 dimensions, right? And so I can get a fit where every essentially the same length, or at least proportional to its strength, because you can use valued ties and fit it in the space. The place you've seen this before is either multidimensional scaling, so that's exactly what a multidimensional scaling is. It's also the distance map on the road map, right? In the old fold paper road maps you pulled out, right? Where you say that DC is a certain distance from Charlotte, which is a certain distance from Miami. And if you feed a network of highway distances to an MDS, you'll recover the United States map. That's exactly what this is doing, right? So it's just back generating a latitude and longitude from a distance mileage chart. And so it's a very slick model. Now there is one fundamental problem with the latent space model for those of us that care about trying to figure out what's going on in networks, is that just like any other clustering routine or factor analysis routine or any of these, I now know where my nodes fall in this dimensions. I don't have any clue what these dimensions mean, right? And so and so if you're clever, here's an old University of Chicago trick, right? So you come up with a really crappy measure and you name it really well, and then you just run with it, right? And so that's what you do here. It's like this is grade, this is education, like this is extroversion, this is introversion, right? This is social capital, this is susceptibility to influence. Name it what you think is most correct, and we'll get your paper published, and off you go. It's never quite that bad. Usually things pop out that are pretty obvious. You go, oh, well, that's gender, right? And so these models are most useful for us in the health world when we don't care what generated the network, but we care about purging the other things that we're interested in, like the effect of gender, the effect of our treatment, or something like that, from the network effects. So we can say, let the model soak up all the variance that I don't care about. Then all those other covariates now are freely estimated and estimated efficiently and consistently and so forth, right? So that's a case where if I don't really care about the network fit, I just want to use that as a way to essentially control away that set and figure out if my other features are driving it. Then that's a really nice job. It's also great from an exploratory standpoint because it lets you figure out whether or not there's what might be driving these dimensions. And there's a third version of this, and I'm surprised that Jake hasn't jumped out of his skin yet to tell us this, which is that where's the other source of the main source of variability probably in network data? These things are measured with error. They're measured like with lots and lots and lots and lots and lots of error, right? So we know that the observed tie we've seen between the set is probably some random realization of a data generation process that is error prone. And so a very nice thing that you can do with these models is ask whether or not people fit in this network, which is essentially giving you a spatial representation of the best, highest probability for ties between nodes. And so you can use that as a way to smooth, essentially, the kind of missing data you're reading. And if you're really clever, then you fit a diffusion model over the top of this, and you have a paper coming out in sociological methods and research, sociological methodology that does this, and you also make it one of the major chapters of your dissertation, right? Right, Jake? Right, exactly. We're hoping, that's where we're at, okay. But this is another thing you can do, right? So especially if your data are messy, this is giving you the best fit to the entire collection of messy data, and probably sort of weakens the reliance on unreliable, binary, on-off, perfectly measured data, which is the assumption built into a lot of our diffusion models. Now we can say, let's generate a network as a posterior distribution from the latent space, and then figure out how likely it is that something would diffuse through this network in general, right, as opposed to a single realization. Please.
I guess I'm a little confused about the groups. Are they, so if I think about this like, if this is school network and this is grade, like this is 7, or is this race, white, black?
The group is a set of people for whom the number of ties internal to the group is more likely than between the groups. So it's a classic sort of community detection sector group. And it's a rescaling for the distance within that set. So it's an interaction between those two. So you're allowed to have, it's essentially adding a separate way of thinking about the latent space. So it's not just that we're collected, but also that we're the distance interacts within the group could be different than the interaction between the groups. So it provides more flexibility, if you will, in the shape of the space. Please?
How is this different than blouse space, or is blouse space the same?
I would turn it around and say the other way. Is
okay.
That what these models are doing are most likely tapping elements of blouse space.
Okay.
Right? Ideally, elements that, well, not always ideal or not, but often elements that we may not have measured. Right? And so if I can add race into the model, I can add grade, I can add education, I can add all those observed covariates, What you're really getting out of the latent space then is the similarity between pairs that isn't already captured by your observed covariates. So it does a nice job of controlling for those things in the network that are evident in the pattern of ties that are not evident in the observed covariates. Awesome. Questions, comments, thoughts, concerns? Going once, going twice. Are we all asleep? All right. All right, let's go up, take a quick break. Then we're going to do, Jake's going to go over some of the randomization procedures in R for us, and maybe some of these kinds of models for those who still have the stomach for hanging out and doing it.